Number 22.
Yeah.
An 82 kilogram painter stands on a long horizontal board 1.55 meters from one end. This 27 kilogram board is uniform, 5.5 meters long, and supported at each end by vertical posts. What is the magnitude of the total force provided by both posts? Okay, so let's draw out our board and our two posts. So where's the center of gravity of the board?
Right in the middle.
Yep. Keep in mind that it's uniformly distributed. We can correctly assume that the center of gravity is going to be smack dab in the middle. So we know that gravity, we can visualize acting just on that point. So we can say there's a force of gravity right there equal to the mass of the board, which was 27.
Mm-hmm.
Times gravity, which is 9.81. So that's some number. We also have a painter standing on the board. Where is he standing?
Stands on the 1.55 meters from the end.
Doesn't matter which end, right?
Mm-hmm.
So we'll say it's like about here. So he's standing on the board. So gravity is also going to be acting on him. And that force of gravity is equal to his mass, which was what?
82.
82 kilograms is 9.81 meters per second squared. So we get 27 times 9.81. So here we had 264.87 newtons of force just pulling the board down, and then we have another 804.42 newtons of force pushing the painter down onto the board. So we know one of our main tools that we use when we do static equilibrium questions like this is the sum of the forces need to equal 0 if we're going to be in static equilibrium. We assume that we are because it doesn't say anything about the board collapsing or the supports giving out or anything like that. So we're assuming that everything is static. So in order for the forces to equal 0, if we have this plus this, so what does that end up being? 1,068 or 69 something. So 804.
You divide that by 2?
No, we just add these two things.
Well, that's how much force is pushing down, right?
Mm-hmm.
So that's how much force the legs may be pushing up. Correct?
Uh-huh.
But isn't it distributed unevenly between the two legs? Because okay. I just forget the equation.
But it's not asking for each leg, is it? Isn't it just asking?
What's the magnitude of the total force? By total force.
Yep. So if we've got this many newtons pushing down, then we know that we have to have that many newtons pushing up. And yeah, you're right. There's for sure, this post is definitely bearing more weight than this post because our painter is closer to this end.
Yeah. Okay.
But the total force is going to have to be that much force down, so there has to be that much force up. So the answer is 1,069.29 newtons.
Okay, so the second question for that would be what we were just talking about. With what force does the post that is closest to the painter push upward on the board?
Okay, so now we'll want to start using our other tool with static equilibrium, and that is sum of torques also must equal 0 if static equilibrium is being observed. So if we select, let's select this side as our pivot point.
Mm-hmm.
We know that over here there's going to be some force acting up counteract all of these forces that are acting down. And so now we can go through and we can calculate the different torques that are being applied at these three significant points. There's also a force that's going on between this post and this board here. So there is, some upward vector that we could draw as far as a force being applied, but the torque at this point would be 0 because torque is equal to the force which is perpendicular to the distance between the axis of rotation and where the force is being applied.
So
And
now
so
we
since this is the axis of rotation and it's where the force is, the distance is 0, so the torque is 0.
So now we just go sum of the torques equals whatever force is times the distance from that pivot point plus the next force.
Yeah, so we have to keep in mind, so these two will add together because they're both trying to get the board to rotate that way. This one is trying to get the board to rotate the opposite direction. So what we want to end up seeing is this plus this has the same torque as this by itself. Does that make sense?
Yeah. So you're gonna add those two, then subtract the other one. Is that what you would do? Are they gonna be different?
So we'll add these two, and then we'll just say whatever that number is the torque
Has to be.
up here, going up.
Okay.
So how do we do that? We know that this is a 5.5 meter board. Is that what it was?
1 point.
So 5.5 divided by 2 is 2.75. So that first point is going to be 2.75 times the force down.
Yep.
Which is 264.9.
Good. So the torque at this point will be
Times 264.9, 728.5.
728.5 Newton meters.
And then the other point is going to be 5.5. Okay, so that's 4 times 804.4. 3,217.
2,317.6
Mm-hmm.
Newton meters.
Sweet. What did I say?
So 4 meters, so that's the distance from here to here, times 804.42 newtons, because that's the force.
Oh.
Is that the right number?
No, oh, sorry. 3217. I don't know what I said. I think I said
3217?
3217.6.
Is that 804.42 times
4? Is that what you got? 804.4
Oh, yeah, there you
times 4. Yeah.
go.
So then we add those two together, you say? And that's how much force is being pushed down.
Oh, but it's not quite 4 meters, right? Because he's
3.95.
1.55 meters away from the edge.
Oh, jeez, what was I? 1.55. Didn't see that 1.55. Dang it.
So it's 5.5 minus
Because it should be
1.55.
3.95.
Yeah.
Okay.
So this should not be 4, it should be 3.95. So it'll,
It's close, it's 3177.45 or 46.
what was it?
3177.46.
3177.46 Newton meters.
728.5.
Cool. So now we know that our total torque trying to push the board counterclockwise is going to be this number plus this number.
Mm-hmm.
So 3177 plus 4.46 plus 728.5. So that means the torque up here must equal 39,000 or 3,905.96 Newton meters. But it's not asking what the torque is at this post, it's asking what the force is. And so we know that torques equal force perpendicular to distance. So since we know the distance between our axis of rotation and where this torque is being applied is 5.5, we can just divide this number by 5.5.
So it's gonna be torque divided by distance equals the force.
Good, yep.
That's the answer. Perfect. That's good.
Did you have what the correct answers are? And those
Yeah,
matched?
those are right.
Those are it.
Okay, how did we get the 728.5 that torque?
So we took,
264.
yeah, the force times the distance, so we know the
Oh,
distance
times the
was.
half of it, okay.
5.5 divided by 2, so,
The 2.75.
yeah.
Did you get the last one right?
I didn't. Yeah, we can do that one.
Cool, any questions here?
No.
See how fast we can do this last one. I got